Hi everyone. Today we are going to do the layout of CMOS inverter. As in the previous video, we have designed and simulated the CMOS inverter in Cadence Virtuoso. So I will be extending the same design to do the layout. So let me open the terminal, give the command. Wait for a few seconds, and the log file is open. Expand it. Now, in Cadence I will open the same schematic that we had created in the last video. So I'll go to the same library that I used, the inverter, and then here I'll create a new layout design. So I'll name it. Wait, I have to open first. So let me open this session, and the schematic is open that we had designed in the last video. And I have to extend this design to the layout. So I'll go to create, not create, I'll go to launch, and then layout Excel, layout create new and automatic, okay, and change the name of the new layout to be design. So I'll name that LOT. So press okay. Session, and yeah, the layout editor is open. Here we have to import our designs and connect the pins or the designs to this layout editor. So I'll go to generate all from source, change the minimum separation to 0.12, and then IO pins. I have to keep all the pins in metal 1 format. So I'll apply. So everyone is changed, metal 1 drawing, every pin is changed. Okay, so now click okay. So this is the components that I had, and using these I have to do the layout of CMOS inverter, and this is the workspace we have. So I need to extend this workspace, so to adjust the components. So I will click S and the boundary on the right, and I'll extend that. Similarly on the top, I'll click on it, I'll expand it to adjust the design, and this is okay. Now I have to bring my all the components inside the workspace. Just select it, drag it to the design. Okay, so before doing the pin placement, press E, the shortcut key E, to get display options, and change this Y and X snapping to 0.05, and same for this, and press OK. Now go to place pin placement, and then here place as in schematic, and for VDD and VSS I will be using the horizontal rail, VDD and VSS, and press close, and you can see. Now do the alignments of the PMOS and NMOS. Okay, now press shift and F to get the names of the terminals of the PMOS devices or NMOS devices. So you can see we have source terminal, we have body, and then we have drain terminal. Then the name of the terminals are shown. Now click on the device. I have to detach the body of the both the PMOS devices and NMOS devices. So I'll click, I'll select the device, press Q, and go to parameter. Wait, press Q, go to parameter, and then body type. It should be detached. Then for PMOS, I will be using in the top of the device. So deselect this and select top tab and press OK, and you can see the body is not detached from the device. Similarly for this, press Q, do body type, detach, and this time I will be do it in the bottom tab. Okay, and OK. So this is the design we have. So now I have to connect all the poly layers, metals, and all. So first of all, I will be connecting the poly layers. So let me make the alignments more straight for both the poly. Now it's straight. So I have to connect the poly. So I'll go to create, shape, and then polygon or rectangle you can choose. Let me choose rectangle. You can also use the shortcut key R, and make sure the poly is selected here. So I will select poly R, zoom it, press Q, and yeah, the gate is connected, the poly layer is connected to each other, and this is the input terminal. So I have to connect this input terminal with this V input, but this is of poly type and this is the metal 1 type. So to connect the metal and poly we need a wire, so use shortcut key O, or also you can go from this way. You can get wire, rotate, close, hide, zoom, and correct the alignments. Okay, and then use the shortcut key P for getting the metal, or you can also go through this way, create, wiring, and then wire. So I will be using the shortcut key P. So P, metal is connected, and then to connect the poly I'll again use R and make sure again the poly is connected. R, zoom it, and from here to here the V in terminal is connected to the wire to the metal. Now again use the shortcut key P to connect the source of the NMOS, PMOS, to the VDD along with its body terminal. Again for this PMOS, the source should be connected to the ground along with the body of the NMOS. So I'll connect this to VSS, and the drain of PMOS and NMOS should be connected. So I'll connect like this, and this is shorted to the output. This is where the output is taken. So I'll again click P and I'll connect this, and now my design is ready. You can see all the terminals are connected properly to their respective nodes. Now I'll have to do the LVS and DRC check. So I'll go to Asura, attach the first of all let me save this. The design is saved now. Go to Asura technology. I've already attached the technology, but let me show you again how to attach it. Click on it, back to the directory. When home directory is shown, go to Cadence, Foundry, Analog, and then 19 nanometer, and then Asura Tech Library, and press OK. And the not library or the technology file is attached. Press OK. Now go to Asura. We will first do the DRC check, which is design and rule check. So please click run DRC in inverter layout. Name is correct and everything else is correct. Just attach the technology, it's already attached. Press OK and wait for few seconds. The DRC run is in progress. Click OK. Yes, you can see metal 1 area must be greater than 0.07 micrometer. So there is a one DRC violation. So I'll click on this and click on this. So it will take me to the place in the schematic or the layout schematic where the things are going incorrect. So I have to extend or increase the area of this metal 1 wire. So for what I do, I'll delete this, and I'll delete this, and I'll extend the wire few part rights. Now again select P, attach the metal, again press R, make sure poly is connected, and from here to here. Now I've changed the layout design, I've changed the area of this wire, the metal 1 wire. The PR boundary is went back. Let me attach the PR boundary. Go to this PR objects and PR boundary. From here, yeah, again save the design. Technology is already selected, I think. Yes, go to Asura, again run DRC. File is already selected. Press OK, and again wait for a few seconds. Yes, override, and wait for a few seconds to get the results of the DRC run. And yes, I want to see the results of this run. Yes, no DRC error found. Now after DRC design and rule check, I have to do the LVS check, which is layout versus schematic. So go to Asura, run LVS, make sure here the schematic design source should be the schematic that we are using to extend it to our layout. So this was the name of my schematic, inverter schematic. Now layout is selected, everything else is selected, technology file is selected, and I'll go to okay. Yes, all right. LVS is in progress. Yes, okay, I want to see the result. Wait for a few seconds, it will take some time. And you can see zero cells have mismatched, zero cells have zero label open problems, schematic and layout match. So this is total DRC violation, which is 0. So yes, I want to see the final result. You can see the debug tab, which is showing schematic and layout match correctly. So yes, and can disclose it. So this is this was the DRC and LVS check. Now I have to do the RC extraction. So for that I will do the Quantus run. So go to Quantus, run Quantus. Now technology is selected, extracted view, correct. Now go to extraction, choose RC extraction, it is already selected, and check the reference node, it is VSS, good. Temperature is correct, the room temperature, and now I'll do or I will press OK. Yes, okay. Again wait for a few seconds. Yeah, Quantus run completed successfully. Close this because the cell is inverter layout and the view is AV extracted, so I have to open this cell. So I'll close this, I'll go to log file and I'll open the AV extracted view. So file, open, inverter library, cell is LOT and AV extracted view. Press OK. And this is how RC extracted view of inverter looks like. You can see, press shift and F and everything will be seen. You can see the value of the resistors, the resistances, the value of the capacitances in standard units like Faraday or ohm. So this is the resistances and capacitances offered by the different junctions and nodes of the CMOS inverter. You can see this is in 83.45 ohm by a polysilicon, and for a metal you can see it just 10.3267 ohm. And we have already we also studied in theory that the polysilicon have more resistivity than the metal, so you can verify this also. So this was all about the CMOS inverter layout design. This is the RC extracted view after Quantus run. So thank you. We will be doing the pre-layout and post-layout simulation verification in our next video.